We don't know. In fact, here we were going like that only. It's doing something to the hypothesis to get a conclusion, then doing something to that conclusion to get even something else. Here, however, we do not seem to be able to do anything to this to get this. But here, hypothesis is true, conclusion is also true. So this is a valid statement, and this is a valid implication, and it's a true implication, because truth implies truth. That's when an implication is true. If we had written something like this, then this implication would be false, but still it's an implication. Okay. There need not be any causal relationship. You can in fact write here something non-mathematical. For example, New Delhi is the capital of India. Then that is also a true statement. There need not be a causal relationship between the statements, between the hypothesis and conclusion of an implication. That is one point which, because of the way we use implication in mathematics, it seems like there should be a causal relation. That's not the case. There may not be any relation. All we want to have is two well-defined mathematical statements on both sides, and so that we can determine their truth values. That is enough. Okay. Now, let me state a peculiar proposition and prove it. Okay. If then you can see that here 2 plus 2 equal to 5 is false. 4 plus 4 equal to 10 is also false. But if it is an if-then statement, in other words, I can write it like this. So this is the hypothesis of the statement, and this is the conclusion. The hypothesis is false. So that means the implication is vacuously true. So although we have started with a false statement and we have obtained a false statement, this is a true statement. So you see the peculiarity of the situation. We have an implication where both the statements are false, but the implication is true because of vacuous truth. But you may be shouting at me at this point, why is vacuously true statement true? So we will come to that. I have already told you that this truth is a matter of convention. It's a convenient convention. In fact, we do not need this, but it's a convention that is very useful. I want to show that usefulness. So this was, of course, not useful in any way, but I just wanted to show that this is a legitimate mathematical statement which is true in spite of how wrong it looks. Okay, now let's come to the serious thing. A theorem. Okay, if n is an integer, then n times n plus 1 is an even integer. Suppose we want to prove this theorem. This is a theorem about integers. If you recall, integers are whole numbers, non-fractional numbers. They can either be positive or negative or zero. That does not matter, but they are not fractions. Things like this: -3, -2, -1, 0, 1, 2, 3, etc. These are